Hi, Mr. Tarou. Let's take a look at a setting that sounds almost like a binomial distribution or a binomial setting. That is a geometric setting. So you're going to read the questions, and again, for every trial or observation, there's going to be two possibilities, a success and a failure. But every time you read a problem, like shooting free throws, answering questions on a test where there's two possibilities of success or failure, right or wrong, it is not automatically binomial. And it actually could be neither binomial or this particular setting we're going to talk about, which is the geometric setting. In a binomial setting, there are a set number of trials. I'm going to ask 300 people a particular question. I'm going to attempt 50 free throws. I'm going to take this test and there's 30 questions on it. Whereas in a geometric setting, you go until your first success. I'm going to ask people a question until I get my first person to say yes. I'm going to play the lottery, and I'm going to keep playing until I get my first win. I'm going to have children, and I'm going to keep going until I have my first boy or my first girl. That's a geometric setting. So a geometric setting has 4 checks, just like binomials. There are 2 outcomes, just like a binomial setting. All the observations must be independent, just like a binomial setting. You must have a constant probability of success. So this is like, you're not taking a multiple choice question, and some problems have 4 choices, some problems have 5, some problems are true and false, which only give you 2 chances of success. You're not getting help in between your trials. Every trial has to have the same probability of success. And the only difference between a geometric setting and a binomial setting is this 4th check I've labeled, which is the variability of interest is not, like in binomial settings, it's a set number of trials. Well, here the variable of interest is to the number of trials it takes before you get your first success. So I'm not very good at free throws, so I'm shooting free throws. I'm going to attempt to shoot until I make my first basket, so I might miss, and then finally make a basket. That would be an example of a geometric setting where I had to go to my 4th trial before I made my first basket. No need for many fancy formulas when you're dealing with a geometric setting because there's only one combination of observations. You have to fail, and the idea is you're going until your first success. So all the initial trials or observations need to be labeled as failures, and your last observation, your last trial, is that first success that you actually achieve. All right? So let's go to page 2. Okay, so let's start doing some examples. Probability, my first success is on my nth trial. Well, I'm giving you a formula, even though I just said there's no really need to have one, but most students do understand probabilities for geometric settings right off the bat. The probability that x equals n, the probability your first success is obtained on your nth trial, is the probability of basically failure raised to the n minus 1 power rate and then multiplied by p. So basically like the basketball example I just said. My chance of failure, and I miss, and that's 3, and then on my 4th trial, I get my success. So an example, even though I just gave you one, an event has a 15% probability of occurring. What's the probability that your first success occurs on the 7th trial? And I'm going to keep this the basis of this example through the rest of these notes, so keep a note of that. Well, if your first success is going to occur on your 7th trial, then the first 6 must be labeled as or considered failures. So the probability that x equals 7, the 7th trial observation is the first time or the first success you have. That's 1 minus 0.15 to the 7 minus 1 power times 0.15, and then it comes out to be 0.057. So there's a 5.7% probability you observe your first success on the 7th trial if your probability of success is 15%. Let's take that same setting and make a PDF table out of that geometric setting. So we have x labeled as the number of trials to get your first success, and p of x, your probability of that occurring. So you can either work out this formula, or you can go to the distribution menu of your calculator. I think that should be second distribution. But find the menu in your calculator and do geometric PDF, probability of success, and again, the number of trials until you get your first success. And the probabilities come out to be 0.15, 0.123, and so on, you'll notice that these probabilities are shrinking all the way through this PDF table, and that is because the probability of success is 0.15. You're constantly multiplying by a value that is less than 1. So this is not really truly a valid PDF or probability distribution function or a probability model, because I cannot list off all of the actual events, and the probabilities kind of go off indefinitely. I mean, in theory, I could just keep going and going and going forever, in theory, and never have my first success. So the partial sum of this, attempted PDF table will always be less than 0. The infinite sum is going to equal 0. Equal 0? Less than 1. Let's try that again. The partial sum will always be less than 1. Only the infinite sum would actually equal 1. And a histogram, if you were to make a histogram, and in this case it would be a relative frequency histogram because these are percents. If you were to construct a histogram out of these values, it would always be a right skewed distribution. You can see these high values on the left, and then they're dropping and dropping and dropping as we go off. So kind of, I would say that we're setting up a PDF table, but we've got these dots here, and really in theory it goes on indefinitely. Well, what if we said that we were only willing to go up to 7 trials until we get our first success? Well, now x here is going to be defined as the number of successes. I should have wrote that definition down, and I just said that incorrectly. X is going to be the number of trials. Okay? What if you were only willing to make up to 7 attempts to try and get your first success? Well, x now cannot be labeled as the number of trials until I get my first success, because I've written in this example that we're just going to give up after 7. So x is going to not be the number of trials before your first success, but simply the number of trials taken. Well, all these numbers are going to match my previous PDF table up here, except for the last one, which now jumps from 0.06 for 7 trials to 0.384. Well, that's because the problem states that we're going to attempt to get our first success, but we're not going to try after 7. We're just going to give up. Well, this now is no longer a geometric setting because, well, it starts off being geometric. We're going to go until our first success. As soon as you say we're going to quit after 7, the whole test of it being geometric falls apart. You are not going until your first success. You're going until you get to 7. And if you don't get your first success by then, we're going to go ahead and quit. So this is no longer a geometric setting, and it's also not a binomial setting because, again, n was not fixed. I mean, if we do get our first success on the first trial, we're going to quit. So this is a probability distribution model for x defined as number of trials, but it's neither geometric nor is it binomial. All right? Page 3. Okay, last bit of notes for a geometric setting. How do you find the mean and the standard deviation of a geometric setting? Well, the formula for the mean of x is 1 over p, and the standard deviation for a geometric variable is the square root of 1 minus p divided by p squared. Now, a little bit funny about the standard deviation formula, and it's just an intro to statistics book that I'm dealing with and I'm helping you guys with. So, we just said that geometric distributions are always right skewed. So this is kind of like an oddball standard deviation formula. You're not going to have a geometric setting that is going to be normal. So just be aware of that. The probability that it takes more than n trials before you see your first success. So instead of like the previous example where I went up to my, I had to go to my 7th trial to see my first success. If I wanted to know the probability that it took more than 7 trials until my first success, there is a formula for that, 1 minus p raised to the n power. I do not believe, no, this is not on the AP formula sheet, so if you want to use that formula in a test, you'll have to have it to memory. And a couple more examples, we'll call it a day. All right? The expected number of trials to achieve your first success. Well, don't forget, expected number of trials is another catchphrase for mean. So the mean of x is 1 divided by 0.15. So again, previous example, 15% chance of success. we should be expecting us to have or have to take an average of 6.67 trials until we see that first success on our last trial. The standard deviation for that piece of data is 6.15. And as an last example, again using your calculator's distribution menu, you can find these commands of geometric CDF, CDF, cumulative distribution function. That's the same as binom CDF if you just watch my video about a binomial distribution or binomial setting. And again, it's only for counts and it only counts down if you're using an 83 or TID4 calculator, Texas Instrument. So the probability that x is less than or equal to 7 is geometric CDF. The probability of success and the number of trials that we're going until we see our first success comes out to be 0.68. And if I want the probability that takes more than 7 trials, well, more than 7, the complement of more than 7 is 7 or less. So I can take my previous answer and subtract it from 1 and get 0.32. Or, if you happen to remember this formula, again, not happen, maybe you study it, but if you do remember this formula, remember it's not going to be on your AP Stats formula sheet, but you can use it. If you remember it, you can use it. The probability that x is greater than 7 is equal to 1 minus the probability of success raised to the 7th power, and you are going to get, of course, the same answer of 0.32. So, I'm Mr. True. That's the geometric setting. Bang! Go do your homework.